Hi guys. So today we are going to start a new unit. We're going to start off by looking at exponential functions. So you might have seen a little bit of this back in Algebra 1. And then after exponential functions, we're going to look at log functions, which are going to be the inverse here. But we're going to start off these first couple of days just looking at exponential growth and decay. And that's what we're going to start off with today. So exponential functions, this is the part you may have seen in Algebra 1. For today, we're going to look at exponential functions in this form, where it's a times b to the x. Whenever we have exponential growth or decay in this form, and this is a little bit of what you guys saw in the intro activity, a is going to be our initial amount, which is going to work out to be our y-intercept. That a value does need to be greater than 0 for the cases we're looking at today. And then b is going to be our growth factor or our decay factor, depending on its value. Now, one thing you'll notice, there's two different cases we're going to look at for today. We're either going to look at where b is greater than 1, or we're going to look at where b is between 0 and 1. And this is something that we looked at again in that intro activity. If b was greater than 1, our function showed growth. If b was between 0 and 1, then it showed decay. One thing we're not going to look at is what's going to happen if b is a negative number. Now, we'll look at transformations to this function later on in this unit, but one thing we're not going to consider is a b value that's negative, because let's say, for example, we had something like this. This is not going to be a function that we're going to graph for a lot of reasons, because think about some of the values that could occur here with different x's. So first of all, think about what would happen as I move from an even to an odd number. Okay, if I do 1, 3, 5, 7, all of those are going to be negative values. So I would start having negative y's here. But then if I do my evens, 2, 4, 6, 8, then I would have positive values. So this graph would bounce back and forth between those positives and negatives. But another problem that would occur here, think about what would happen if that was a fraction. If that was something like 1/2, well, I can't take the square root of a negative number, or 1/4, or 7/4, or 8/2. Well, that's a whole number, but if I took 7/2, okay, I couldn't take the square root of -2. You cannot take an even root, so I'd have a bunch of undefined values on here too. So there'd be positives, there'd be negatives, it'd bounce back and forth, there'd be undefined. It's just not a function that we are going to be able to graph. So we're only going to look at what happens when that base is either between 0 and 1, or that base is greater than 1. Now, if that base were 0 or 1, think about what that would do to your graph. Okay, if the base was 0, well, 0 to the anything is just going to be 0. This wouldn't be an exponential function, it'd just be a line. Same thing if the base was 1. 1 to the anything, okay, that's just going to be 1. All right, so again, it would just be a straight line. All right, so again, the other part here is that growth factor, okay? And so it's a times b to the x. So that's 3 times 4 to the x. That's 7 times 1/2 to the x. One thing you have to pay attention to is we cannot multiply those two numbers together because, again, it's order of operations. The 4 has an exponent, the 3 does not. That is not the same thing as 12 to the x. You cannot combine those two things together because one of them has an exponent and one of them does not. Again, we're going to consider when that a is greater than 0, because if a were 0, 0 times anything is 0, it would just be a line. Now, when we do transformations, we'll consider what happens when that's negative. But just for looking at basic growth and decay examples, we're going to kind of stick to this basic equation for today. We're not looking at transformations. We're just going to consider that function when our a is greater than 0 and our b is a bit greater than 0 and not 1. All right, so all that to say, this is a little bit of what we looked at in the intro. As we plot those points, you notice that there was a horizontal asymptote. Because as you raise that base to a power, whatever that base is, you're not going to end up with negative numbers. You also have your y-intercept is going to be whatever that a value is. In this parent function case, that value is 1. And then it's just going to increase as time goes on. Some of the points that are going to fall on this graph, 0, 1, because anything to the 0 power is 1. 1, the base. 2, the base squared. You also would have -1, 1 over the base, because remember, those negative exponents are going to flip your fractions. All right, decay parent function is going to look similar, but as you guys notice, it's going to go in the opposite direction. We still have that horizontal asymptote, and it's going to go through some similar points. 0, 1, 1, the base, but this time the base is a fraction, so the base is like 1/2, 1/3, 1/4. it still would be 2 comma the base squared, but again, that's why this graph has the shape that it does. Because if you square a fraction, think about if you have 1/2 and you square it, it would become a smaller fraction. So that's why that decay function looks the way that it does. And then the reason it gets bigger towards the left, if you do that negative, it'd be 1 divided by the base. But if you do 1 divided by a fraction, you flip it, it becomes 2. So those negative numbers are going to become larger as it moves to the left for that reason. So that's why your decay function looks the way that it does. So the biggest things to really see for today, if your base is greater than 1, it's going to show growth. If your base is between 0 and 1, it's going to show decay. So we're just going to look at a few basic examples that have that same idea here. Okay, we're first just going to determine, do these graphs show growth or decay? So this first one here is an example of growth because the base is greater than 1. Whereas the second one is an example of decay because that base is between 0 and 1. C is still an example of decay because the base, the thing that has the exponent, is less than 1. This number out in front is just going to change our y-intercept. That's your initial value. All right, and then finally this last one, even though it's a fraction, it does still show growth because the value that has the exponent is greater than 1. Now, if I want to graph these, what I'm going to do is, honestly, I'm just going to show you the basic shape, and then we're going to list the points out. That way it doesn't have to be too perfect. So this one shows growth, so it's going to have this shape, 0, 1, 1 comma the base, and then 2 comma the base squared. If you wanted to, you also could include negative 1, 1 over the base. All of those are points that would be on this graph. All right, let's do decay. Same shape, but going to go in the opposite direction. And again, goes through 0, 1, 1 comma the base, 2 comma the base squared, which would be 9 over 16 and a smaller fraction. And then negative 1, that reciprocal. So 2 is going to look like a similar shape, but that 2 right there that's out in front, that changes your y-intercept. It changes the initial value. Because think about it, if you plug in 0 for x, anything to the 0 power is 1, but now it's being then multiplied by 2. So 0, 2 would be your y-intercept. It is still going to have the shape of decay, but let's just pick kind of 2 points here. Let's plug in 1. 3/4 to the first power is 3/4. 3/4 times 2 would be 3 over 2. If I plug in negative 1, that would be the reciprocal. So 4/3 times 2 would be 8 over 3. So that's a few points that are on there. All right, and this last one again is going to show growth. So it's going to go through 0, 1 again, 1 the base, 2 the base squared, and negative 1 the reciprocal. Whoops, reciprocal of the original. And there were a few points on there. Now, we're going to spend a lot more time graphing here in a few days and looking at transformations. But for now, this is really just getting you used to kind of what some of these parent function points are on this exponential function. The big thing to notice about all these graphs that they have in common, every single one of them has a horizontal asymptote at y equals 0. That means every single one of these graphs has the same domain and range. All right, so the next thing we're going to look at is a new value we're going to see come up in exponential functions, and it is the letter e. So you may have noticed at this point, you've seen a lot of different variables and problems. You've never really seen lowercase e used. That's because lowercase e is kind of like pi. It actually is a numerical value. If you were to use e on your calculator, it would give you a long decimal. That number is called Euler's number. So it's not pronounced Euler, it's pronounced Euler. And that number actually is going to be really important for you in calculus because it has some really unique things about it. E has a lot of really important real-life examples that we'll look at next class. But for today, we're just going to look at what E is. So E, there's 2 different ways you can figure out what E is. But one thing you can use is this little expression here. And the bigger that x value gets, the closer this number is going to get to infinity. So if I plug in 10 into that equation, I'll get a certain decimal. If I plug in 100, 1,000, all the way up to however many zeros you want to plug in. The more zeros you plug in, the closer that number is going to get to what E actually is. So I'm going to go ahead and pause it and write out what these numbers are instead of taking the time to type them all in on the video. All right, so here are some of those numbers plugged into that equation. And what you'll notice, the bigger it gets, the more certain numbers keep repeating. So every single one of these started with a 2. And then from here on over, we always had a 7 after the decimal. Then we always had a 1. And then each time we added a 0, we got another decimal that was another place after the decimal that stayed consistent. So 718, they all had an 8. Then from here on, they both had a 2. So the further and further you get, the more decimals you're going to get. They're going to be more consistent, showing us what this value is. So the way we'll approximate E, it is about 2.718. So that is what E is. Another way you can estimate E is using this factorial formula. If you take all of these factorials and you keep going and add them up as close to infinity as you can possibly get, that's going to give you the closest you can get to the value of E. All right, so what we're going to do is just a quick little exponent review, okay? E is a constant, but we can still follow those same exponent rules because that base is consistent. It is a base. If the bases are the same for those exponents, you can add them together. Here we can divide, which means we can subtract those exponents. This would be 5e, 13 minus 12. Power to a power, you would multiply that as exponents. So this would be 2 to the 5th, e to the negative 15x. Negative exponent would move it to the bottom of the fraction. So when we graph using E, it's a different way to show growth and decay. Again, we'll get more into this when we look at transformations in a couple days. But for exponential growth and decay with a base of E, what's a little bit different here is because that base is 2.7, that base is always greater than 1. So it would show growth if it was just e to the x. We can still show decay with a base of E though. So the way we'd make that different is based on what your exponent is. So if your exponent is a negative, then and the base is E, that's the way that you would show decay. So when we look at just any other base, we just consider, hey, is that base greater or larger than 1? If the base is E, though, we need to consider, hey, what is our exponent? Is it positive or negative? So e to the x would have that same shape as growth, but e to the negative x, if you have that negative up there, that is how you show decay with the base of E. And that's a pretty badly drawn graph, but again, if you think about the reason why, we'll get more into this in a few days when we do transformations. Think about what that negative does. Okay, that negative, that's a reflection over the y. That's why our graph looks the way it does. All right, so all we're going to do now is, just determine, do these graphs show growth and decay? They all have a base of E. Now remember, that number out in front, that's your initial value here. Okay, it's not going to affect your base. We do not multiply them together. So this is E to a negative, which means it's going to show decay. This is e to a positive. Even though there's a decimal out in front, that does not matter. That's not the base. That does not have the exponent. The e is the only thing that has an exponent. It's a positive exponent, so it shows growth. Here we have e, and it's raised to a negative, which means it shows decay. It doesn't matter that that number is larger. That is just your initial value. This is still going to show decay. All right, so now we're going to get into kind of some rewriting, okay? So we're going to start to look at kind of our basic growth and decay formula that we saw a little bit in that intro activity. We're also going to see this a little bit more next class when we look at some applications. So using exponent rules, we can rewrite these functions a couple different ways. So one thing to remember, let's look at this first one, 2 to the 2x. I want to try to rewrite this into this form, a times b to the x. So you'll notice there the x is just a single x. Right now we have a 2 in front of it. So let's consider our exponent properties. When you have multiplication in the exponent, that means you have a power to a power. So this is the same thing as 2 squared to the x. Because again, with your exponent properties, power to a power, you multiply. So that means I could rewrite this as 2 squared, which is just 4, to the x. So that's a way that I can rewrite that using those properties. Okay, let's look at the next one. I have x plus 1. So when you have addition in the exponent, that's when your bases are multiplied. So this would be the same thing as 2 to the x times 2 to the 1. Because again, if you think about what you would do here, same base, you add the exponents, that would give us our original problem. So 2 to the 1 is just 2. So this is 2 times 2 to the x. So a lot of different ways we can use our exponent properties to rewrite this. And again, we'll do this again on another day as well. But what this property allows us to do is to take different functions and rewrite them into this kind of growth and decay format. So the ones we've looked at so far that were in that basic form of like 3 to the x or 2 times 1/2 to the x. What we talked about with that intro activity is that the number here that was raised, that was your growth factor. But then when we looked at it in this format, that showed us the growth or decay percentage, or the rate. So what we're going to do is we're going to take these and we're going to rewrite them into this form so that we can find that growth or decay rate. So this one's going to, all of these are going to use this same kind of property as this first question. So here I have a, which is just regular old a. I have 2 to the x over 3. So that's the same thing as 2 to the 1/3 raised to the x. Because power to a power, you would multiply those exponents. Well, then what I can do is I can get a calculator and I can actually evaluate what 2 to the 1/3 is. So using a calculator, 2 to the 1/3 is the decimal 1.2599. So our growth factor here would be 1.2599. If I want to find the percent growth, I can then rewrite this as 1 plus 0.2599 to the x. So this is showing growth because that is larger than 1. And the percent growth here, this would be a 25.99% growth. The factor there is 1.2599. So if I wanted to keep doing this, I could multiply by 1.2599 each time. The percent it's changing by, though, is that 25.99%. All right, let's try another one. Let's rewrite it. So using those exponent properties, this would be 0.5 to the 1 over 12 to the x power. So let's do 0.5 to the 1/12 in a calculator. If I plug that into a calculator, that's going to give me 0.9439, which now tells me we're talking about decay here because that's smaller than 1. Now I can rewrite it to find the percent change. So 0.9439, that is going to be the same as 1 minus 0.0561. So this is decay, and that percentage would be 5.61%. All right, let's try this next one. Same idea, but we're talking about e. So this would be e to the negative 0.5 raised to the x. Again, get a calculator, evaluate e to the negative 0.5. That is going to be 0.6065. So this, again, shows me that I'm talking about decay here. I also knew that because it was a negative exponent, but now I know exactly what kind of decay we're talking about. So I can rewrite this as 1 minus 0.3935 to the x. So this is a 39.35% decay. All right, last one. If you feel comfortable, pause the video, try it on your own. All right, so 0.5 is just, again, 0.5 is just that starting value. E to the 0.8 to the x. So we can do e to the 0.8 on a calculator. So e to the 0.8 would be 2.2255. So this is, again, showing growth. That's the same thing as 1 plus 1.2255 to the x. So this is a 122.55% growth. Now, if you think about it, the factor there was 2.2. It's like it's doubling, okay, or more than doubling. So 100% growth is doubling. Okay, that's your factor. All right, so now we're just going to look at some tables now that we kind of are familiar with what exponential growth and decay looks like to determine if something is showing exponential growth or decay. Also going to be able to review if it's showing a linear or quadratic model. So let's look and see what's happening to these numbers. Okay, so my x's are changing consistently. And then my y's here, I'm going from 0.5 to 1 to 2 to 4 to 8. I am multiplying by 2 each time. If you multiply by that constant number and your x's are evenly spaced, then that is an example of exponential, in this case growth, but it's exponential data. All right, let's look at B. Let's look at what's happening here. Okay, so this is changing a little bit. We're subtracting 2, we're adding 2, we're adding 6, we're adding 10. I can't really see anything consistent here, but if you remember, if we check the difference of the differences and how those are changing, that tells us that we're dealing with quadratic data. So this would be a quadratic model. All right, next one, x's are evenly spaced, but our y's this time, we're subtracting 3. That is linear. Okay, so adding or subtracting a constant amount is linear. Then our last one here, the x's are evenly spaced, but our y's we're dividing by 3. Well, remember, dividing by 3 is the same thing as multiplying by 1/3, which again is a form of exponential data. This would just be a case of exponential decay, whereas that first one was exponential growth. All right, so the last thing that we're going to do is we're going to write one of these exponential models using 2 points. Now, we talked about a regression when we did that original activity. You also can use regression to check your answer here. As long as you have those 2 points and you know that it's exponential, you can actually check that model by using regression and getting exactly what that is. Now, we're going to do this without a calculator. We're going to use some algebra to figure this out. So we want to write this equation in the form of y equals a times b to the x. I do not know a, and I do not know b. Well, if I have 2 missing variables, if I write 2 equations, I can set up a system. And that's exactly what I'm going to do. I have 2 different x's and y's. So I'm going to plug those in for x and y to write 2 equations and then solve my system. So if I plug in y, and then b to the first would just be ab. Then we'll plug it in here. 54 is equal to ab to the third. So now all I have to do is solve this system, and then I'm able to write my model. So I'll solve for one of these variables. I'll just get a by itself. So that would be 6 divided by b. So 54 would equal 6 divided by b times b to the third. So 54 would equal 6 times b squared. Divide by 6. Now b technically here, if we're just solving this equation, could be plus or minus 9. But remember, when we talked about these exponential functions, the base is not going to be negative. Okay, the base is going to be just the positive version here. So we can just say base is 3, or b is 3. Once we know b, we can plug it back in order to get a, and I get that a is 2. So this is 2 times 3 to the x. All right, if you feel comfortable, pause the video, try this next one on your own. All right, so let's set up our system. So 12 is equal to a times b to the negative second. 48 is equal to a times b to the negative fourth. And remember what negative exponents do. They move it to the bottom of the fraction. So I'll just rewrite this. This is a over b squared. And this is a over b to the fourth. So let's go ahead and solve for a on one of these equations. I'll solve for it on the top one. So a would be 12 times b squared. Let's plug it in. 48 would equal 12b squared over b to the fourth, which means that 48 would equal 12 over b squared. So 48b squared would equal 12. B squared would equal 1 over 4. When we square root the top and bottom. And again, the negative is not really going to be in effect here because our base is going to have to be the positive value. Now we know b. Let's plug it in to get a, either equation. So I'll go back to the original, because I think it's a little bit easier to see it with that negative exponent. 1/2 to the negative second, you would flip that fraction. So that would become 4. And I would get that a is 3. So 3 times 1/2 to the x. Again, remember, we cannot multiply the base and the a value together. They are separate for a reason. One of them has an exponent and one of them does not. All right, so that is it for exponential growth and decay. Next class, we will look at some applications. And then after that, we're going to look at transformations.